Okay, so this problem says to start a car engine, the car battery moves 3.75 times 10 to the 21 electrons through the starter motor. How many coulombs of charge were moved? Okay. So this is you can look this up in a table. The charge of an electron, and again this is just the magnitude of the charge, is 1.6 times 10 minus 19 coulombs. Okay. So the total charge that was moved through the starter motor is Q, the total charges, and you saw that charge is quantized. All the charge that you can get in the universe is an integer multiple times the fundamental charge, and that's an integer. Yep. So 3.75 times 10 to the 21 times 1.6 into 10 minus 19 coulombs. Okay, that's 10 to the 2, 375 times that. Okay, so 600 coulombs. All right, so later on you will sort of see that a thundercloud, where you have charge separation in a thundercloud, this charge separation can be about 10 to 20 coulombs. So this is about 10 times the charge separation in a thundercloud. All right, so that's a very large charge. And also, when we come to DC circuits, you'll see that to start a car motor, you pass about 200 amps of current. The current is about 200 amps. Yeah. All right, so this problem says, suppose a speck of dust in an electrostatic precipitator. So you saw how these things work. These precipitators remove all the particulate matter, and if you have a precipitator, this is the smoke that you get out. Okay? Electrostatic precipitator can clean up all of that. So suppose a speck of dust in an electrostatic precipitator has 10 to the power 12 protons in it and has a net charge of minus 5 nanocoulombs, a very large charge for a small speck. Okay, so here it's got multiple, actually a billion protons, a trillion protons. So the charge is n times E. Okay. So why do they call it a very large charge on a small speck? Why is that? These guys want to repel each other. Okay? So it's very hard to hold on to such a large charge. How many electrons does it have? Okay. So suppose a speck of dust. Oh, wait a second. Has 10 to the 12 protons in it and has a net charge. Okay, sorry, I was reading it wrong. Okay. Oh, all right. So this thing has a negative charge. Okay. What it's telling you is it has 10 to the 12 protons. So let's say it's made of carbon. Okay. Then that tells you how many carbon atoms this has. Okay. So each carbon atom has 6 protons. So you would divide that by 6 and you'd get the number of carbon atoms. Okay. Has a net charge of minus 5. So Q is minus 5 nanocoulombs. So Q is N times E, N is Q over E. Okay. So the number of electrons, excess electrons that it has is, and this time since the charge is negative, we'll put the negative charge of the electron. So what this number tells you is the number of excess electrons it has. All right, so this is, you get 10 to the power 10, 5 divided by that. Okay, so this was the excess charge. If the number of electrons were equal to the number of protons, it would be neutral. But the excess electrons is what gives it a negative charge. So it has a net charge of that. How many electrons does it have? So the number of electrons the spec has are 10 to the power of 12, that's how many protons it had, plus 3.125 into 10 to the power of 10 electrons. Okay. That's what contributed to the excess charge. So this is equal to 1.03125 into 10 to the power 12. And that's how many electrons it has. Okay. All right. So this problem says, what net charge would you place on a 100-gram piece of sulfur if you put an extra electron on 1 in trillion of its atoms? All right, so the first thing you have to do is find out in a 100-gram piece of sulfur how many atoms you have. And for every trillionth atom, you're going to put an extra electron. All right, so let's look up the atomic mass of sulfur, and that's 32. Okay, so the number of atoms of sulfur that you have are 100 grams divided by 32 grams per mole. And so that's how many moles you have of sulfur. And you, of course, have Avogadro number of atoms per mole. So when you have 100 grams of sulfur, that's how many atoms you have. Okay? So that's how many atoms of sulfur you have. Okay. And what are you going to do? You're going to put an extra electron in every trillion sulfur atom. Okay. So the number of what? What?
So it's 2 extra electrons.
Well, no. So 1.88 into 10 to the 24 divided by 10 to the 12. So 1.88 into 10 to the 12 electrons. So you're going to put a trillion, 2 times trillion electrons. Okay. You guys following this? All right. So this problem says protons in an atomic nucleus are typically 10 to the minus 15 meters apart. Okay, this is a femtometer, okay, after Mr. Fermi. What is the electric force of repulsion between nuclear protons? Okay. So here are two protons, and the distance between them is 10 to the minus 15 meters. Okay. The force of repulsion between them is given by this formula K Q1 Q2 divided by R square. Okay. K is 9 times 10 to the 9 and the charge of the two protons is the charge of the electron, which is 1.6 times 10 to the minus 19 coulombs squared, and then 10 to the minus 15 squared. Okay, so let's take care of powers of 10. That's 10 to the minus 19, and that gives you 10 to the minus 4, and then that's squared. Okay, so 10 to the minus 8, but you have a 10 to the plus 9 here, so that becomes a 90. So force is 90 times 1.6 square newtons. Okay, so the force between two protons is 230 newtons. Okay, this is almost half your body weight. A tiny proton is being repelled by half your body weight. I mean, that thing should fly away. So why isn't it flying away?
Because of the even stronger force.
Because of the strong force. Okay? So the strong force is 100 times greater than this force. Okay, so the strong force is pulling back with a force of 23,000 newtons. Okay, that's 50 times your body weight. Okay. But what is the nature of this strong force?
The range is really short, right?
The range is that much, and so that's why all nuclei are that tiny. Okay, so that's why they don't fly apart. All right. This problem says two small balls, each of mass 5 grams, are attached to a silk thread 50 centimeters long, which are in turn tied to the same point on the ceiling as shown below. Okay, I guess I don't have that. When the balls are given the same charge Q, the threads hang 5 degrees to the vertical as shown below. What is the magnitude of Q of each? Okay, so I guess I'll draw them. This is 0.5 meters. This is 5 degrees. So this distance is 0.5 sine 5. And so R is 2 times 0.5 times sine 5. This, oops. that is R. So let's figure out R. R is 8 centimeters. Okay. So what is it that we have? Okay, so in this diagram, so there is the electrostatic repulsive force, there's the tension in the string, and there's the force of gravity. Okay. Those are the three forces that are balancing each other. Okay. This is 5 degrees. Okay. All right, so you can see that the x component of the tension is balancing that force, and the y component of the tension is balancing this force. Okay, so let's do that. And by the way, our x and y axis are like that. So T cosine phi equal to mg, and T sine phi equal to the electrostatic force. So if you divide this by that, tan phi equal to the electrostatic force divided by mg. So mg times tan phi equal to k q square divided by r square. The electrostatic force between these two guys is their charge, and each charge is too small, are attached to the thread. What is when the balls are given the same charge q? So this is q and that's q. Okay, so q square is r square mg tan phi divided by k. All right. So let's copy this. Okay, so now we'll put in the numbers. So Q is 0.087 square. M was 5 grams, 5 into, yeah, each sphere is 5 grams, 10 to the minus 3 kgs. G is 9.8 meters per second square. Tan phi, and K is 9 times 10 to the 9. Okay, so what I'll do is, so this becomes 10 to the minus 12, to the power half of 10 to the minus 6. The charge, units of the charge are coulombs. I'll bring that out as well. So 0.087. And then what we have left is 5 times 9.8 times tan phi divided by 9 to the power half. Okay, so let's figure this out. All right, so this works out to 0.06 into 10 minus 6 coulombs, which is 60 into 10 minus 3 coulombs, 60 millicoulombs. So that's the charge on each sphere. Okay. What would happen if you increase the charge on the spheres?
They would go even further apart?
That's right. Okay, very good. Okay, we'll do a couple more problems. I'll show you an integral. All right, let's do this one. So on a typical clear day, the atmospheric electric field points downward and has a magnitude of 100 newtons per coulomb. So the electric field is 100 newtons per coulomb, pointing downwards. Okay. Compare the gravitational and electric forces on a small dust particle of mass 2 times 10 to the minus 15 grams. So you have a small dust particle, mass is 2 times 10 to the minus 15 grams, okay, that carries a single electron charge. Okay, that's singly charged. Okay, here's the problem. So in what direction is the force on this guy? I'm sorry? So there is the force of gravity, and the electrostatic force is Q times the electric field. The charge is negative, okay? And so the electrostatic force is in that direction. Okay, so why do we care about this? See, this particle, if it gets charged, there's an electrostatic force in that direction, and now this can float around. Okay, if this force is greater, it'll, well, anyway, it can hang around in the atmosphere a long time. And so if it's an allergen, that's not a good thing. Okay. So now they want you to find the acceleration of the dust particle. Okay. So let's say we'll assume that this force is greater than that, and we'll choose that as the positive direction. So the electrostatic force minus the gravitational force is mass times acceleration. And if this acceleration turns out to be negative, then that just means that this force is greater than the electrostatic force. Okay? All right, so is E times E minus M times G over M. So here's the acceleration due to the electrostatic force, and there's the acceleration due to gravity. All right, so let's put in the numbers. So A is, the charge is 1.6 times 10 to the minus 19 coulombs. We're just doing magnitudes because we put in all, we've drawn in the diagram, we have given the directions, okay? And the mass is 2 times 10 to the minus 15 kgs with 15 grams, which is minus 18 kgs. Okay, so that 18 cancel that. There's minus 1, that's 10. So 16 by 2, 8 minus g. Okay, 8 meters per second squared is the acceleration due to the electrostatic force. So gravity is slightly greater, so it's still falling down. Okay, but it takes a longer time to settle. Yeah, so 8 minus 9.8 equal to minus 1.8 meters per second squared. That's the acceleration due to gravity on the moon, roughly. Okay. So that dust particle will linger around in the atmosphere. That charged dust particle. Okay. In this problem, they say the electric field in a particular thundercloud is 2 times 10 to the 5 newtons per coulomb. What is the acceleration of an electron in this field? By the way, more than half the lightning is intra-cloud lightning, intra and intercloud lightning. Okay. Is this a large enough electric field to create lightning? Do you guys remember the number? 3 million volt per meter, or 3 million Newton per coulomb. Okay. So this is not quite enough. So the cloud needs to build a little more charge before it can have lightning inside. All right, the force is given by E times E, and that should equal mass times acceleration. So the acceleration is the charge of the electron times the electric field divided by the mass of the electron. The charge of the electron is 1.6 times 10 to the minus 19 coulombs. The electric field is 10 to the power 5 Newton per coulomb. And the mass of the electron is 10 to the minus 31 kgs. Okay. All right, again, you want to take your powers of 10, that comes up there, it becomes plus 31, so plus 12, plus 5, 17 meters per second square. All right, so the acceleration of the okay, and if you divide that by 0.98, okay, so okay, so again we write it like so because that's 1,000 trillion, 4,000 trillion G's is the acceleration of the electron. So what does the electron do? It speeds up and then collides with one of the molecules in the thundercloud. Okay, and before it collides with the air molecule, it hasn't picked up enough speed to knock off electrons. Only when you're going fast enough to knock off electrons and make the air conducting, that's when lightning can happen. Okay? So even though this is a large acceleration, that acceleration is not large enough. When this field gets to be 3 million volts per meter, so 10 times greater, when the acceleration is 10 times greater, then it can start knocking off electrons. Okay? All right, let's do one more problem. Okay. Okay, so this problem says a total charge Q is distributed uniformly along a thin straight rod of length L. So this is uniformly distributed. So how much charge is there on this length? Okay, so dq, the charge on that is dx by L times Q. Okay? So we'll call this x and so on. What is the electric field P1 at P1 and P2? Okay, so so the formula for the electric field is KQ divided by R squared. That's the magnitude of the electric field. Okay, it's given by that equation. Okay, what do you think is the electric field at that point, at the center? What would your guess be? Okay, so here,
Same across the entire.
no, so here's how you look at it. So break this up. This is what you would do in calculus. So there is the center point, there is the center point. Okay, so we have equal charges. Let's say Q is positive, and the argument would be the same if it were negative. So this positive charge has an electric field in this direction. This positive charge has an electric field in this direction. They're equal charges and they're equidistant, so this cancels with that. So corresponding to every little charge, you have a corresponding charge that's canceling the electric field. So, very good. So the electric field at P1 is 0. Okay, so that's what you learned from symmetry. Okay. All right. Now at P2, it's a little harder. So let's do that. So now we're going to find the electric field at P2. So now if you break this up, all the electric fields are canceling, except that what is happening for each little charge, the distance changes. So you have to do an integral. Okay, so when you have to sum all of those guys. Okay, so so this is, we'll call this charge dq, and P2, this distance is A. So the electric field due to the charge dq, so due to this charge at this location, again, if you assume dq is positive, so there is dE. dE is dk dq divided by distance square. There is the distance. What is this distance equal to? I'm sorry? R is L plus A minus X. Okay, we have to write it in terms of that. So R squared. And you saw we already wrote dq as dx over L times Q. Okay, so the electric field due to that little element is K. dq is dx over L times Q, and L plus A minus X squared. So the electric field due to this guy has been written in terms of X. And so for the entire rod, you just add up all the electric field due to all these little pieces. Okay, and that's doing an integral. Okay. So E is okay, so we are doing an integral over x, okay? And what does x vary from? This 0 to L. Okay, that's when you run out of charge. Okay? 0 to L. All right, so let's pull out all the constants. K, Q, L, 0 to L, dx, L plus A minus x squared. All right, and you can check this out. The integral of this is just 1 over L plus A minus x. Okay. All right. So this is equal to KQ over L. For the top, that's L minus L, that's 1 over A, minus 1 over L plus A. Okay, so if Q is positive, again, this is bigger than that. So when Q is positive, the electric field will be to the right. Yep. And when Q is negative, the electric field will be to the left. Anyway, here is the magnitude of the electric field. All right, so here's an so let's simplify this further, I guess. The electric field is KQ over L, L plus A minus A, which is L. So L over A times L plus A. The L cancels. A times L plus A. Okay, and so here's a neat thing about it. So in the limit L becoming 0, that'll become a point charge, and the electric field will be KQ over A squared. KQ over A squared. Okay, so it has the right limits. All right, guys, so we'll stop here. That problem is simpler. Okay.